Greetings of the day to all of you. I welcome to lecture number 2 of lecture series on electric drives. Today is Friday, 30th December 2022, and I'm going to deliver this lecture number 2. In our lecture number 1, as you remember, we have already discussed about that lecture number 1 was introductory lecture on this electric drives. We have seen what are the advantages of electric drives and what actually we mean by electric drives. We have also drawn the block diagram and tried to understand various components of an electric drive. And depending upon what type of motor we use, we have classified the electric drives as DC drives and AC drives. If you see the scenario, in the year 1990, DC drives constituted about 40% of total drives used by industries, as compared to AC drives, which formed about 60% of total drives used by industries. In 1995, this figure changed. The use of DC drives reduced from 40% to 30%, and the use of AC drives, it increased from 60% to 70%. Then in the year 2000, the use of DC drives was further reduced from 30% to 25%, and the AC drives applications increased from 70% to 75%. In the year 2005, DC drives constituted only 20% of total drives, industrial drives, as compared to AC drives, which constituted about 80% of electrical drives. This is the data available with me from one of the books. By the year of this year, that is 2022, I am sure that AC drives must have already surpassed DC drives in most of the applications. The use of AC drives must be more than 90 to 95% as compared to DC drives, which may be constituting less than 5 to 10% of total drives. The question is why we shifted from use of DC drives to AC drives. What prompted the industries to shift from DC drives to AC drives? It is because of some significant advantages offered by AC motors over DC motors. For example, if you take AC motors do not use brushes, they do not use commutator, so therefore their initial cost and maintenance cost is low as compared to DC motors. Initial and maintenance cost is low. Okay. Secondly, in case of AC drives, maintenance cost is low because they do not use brushes, they do not use commutators, and also torque density is high. Torque density, which is given in Newton meter per kilogram, is high, which means for a given weight of the AC motor, it develops more torque than DC motor of the same weight. Similarly, the power density of AC motors is high. Power density is given in kilowatts per kilogram. If you take certain weight of DC motor and AC motor, you will find that for the same weight, the power developed by an AC motor is more than that of DC motor. And with the advent of power electronics technology, now AC motors are amenable to very easy methods of speed control. It has become now easy to control the torque and speed of AC motors. These are the reasons. That's why AC motor drives have now almost replaced DC motor drives in majority of the applications, except a few applications. Another very important point that I want to discuss with you in today's lecture is that one of the most important components of electric drive, whether it is DC drive or AC drive, is power processor. I've already discussed with you in the block diagrams last lecture, power processor or power modulator. It is nothing but it is a power electronic converter. Power electronic converter. PEC. What's the job of this power electronic converter? It acts as a power processor. It converts and controls the power. It converts power from one form to another form. For example, it may convert from AC to DC, or DC to DC, or DC to AC, or AC to AC. Okay, and simultaneously it also results in the control of torque and control of speed of the drive, whether it is a DC drive or AC drive. So power electronic converter or power processor or power modulator is very important part of any drive, any electric drive, whether it is DC drive or AC drive. However, when we use power electronic converter as a power processor for the control of electrical drive, the cost of power electronic converter is high as compared to cost of motor itself. There is a ratio C, which is defined as a ratio between price of power electronic converter, PEC, divided by price of AC motor. Price of AC motor. It's the ratio of the prices of power electronic converter and motor, and presently it is 5:2. That means the ratio of price of power electronic converter to price of AC motor in an electric drive is 5:2, which means that the price of power electronic converter is higher than the price of motor, and it makes the drive a bit costly. Its initial cost is high, but it pays off. When you use power electronic converter in an electric drive, it results in flexibility in control, wide range of speed control, wide range of torque control, and it also results in energy conservation. So I will try to discuss with you the energy conservation, which is one of the advantages of using power electronic converters or power processors. Let me try to discuss with you this concept of energy conservation with the help of a simple example. Let us take a motor-driven pump. Motor-driven pump. A motor-driven pump, if it is a conventional motor-driven pump, not using power electronic converter, not using any power processor, it looks like this. You have a motor. It may be a single-phase motor or it may be a three-phase motor, depending upon the power of the pump. So this is AC input, and this motor is coupled to pump. This is the pump, water pump. This is pump. This is the inlet pipe of pump, and water enters the inlet pipe from here, and this is the outlet. We want to pump the water to a certain height. This is the outlet pipe of the pump, and you have a throttling valve here for controlling the flow rate. This is throttling valve. What happens when the motor is connected to AC source? It starts drawing the power. The power drawn by motor is given by omega into T. Okay. When motor is connected to source, it starts running at the rated speed. Since it runs at the rated speed, it draws the rated power, irrespective of what is the flow rate. If the flow rate is high, you keep the throttling valve open so that a large amount of water flows. Flow rate is high. But if you want to reduce the flow rate, how do you reduce the flow rate? You close the throttling valve. You close the throttling valve in such a way that the flow rate from this outlet pipe is very low, okay, depending upon how much flow rate you want. Okay, by closing the throttling valve, we can decrease the flow rate. When we decrease the flow rate, how much is the power drawn by motor from the AC source? It is same, because we are not changing the speed. It's a single speed motor. I will write here single speed motor. I am not using any power electronic converter for controlling the speed of this motor. It runs at single speed. Let's suppose it runs at 1470 RPM, and it always runs at this rated speed, whether the flow rate is high or low. So that means all the time, whether flow rate is high or whether flow rate is low, it draws the same amount of power. When flow rate is high, it draws certain amount of power, no problem, there are very less losses in the system. But when you decrease the flow rate by closing the throttling valve, motor draws same amount of power, but flow rate is low. So where does the rest of the power go? It simply gets wasted. So that means at low flow rate, when you close the throttling valve, okay, when you close the throttling valve, flow rate is decreased, but motor draws same amount of power as it was drawing when flow rate was high. So therefore, this mechanism, this traditional or conventional motor driven pump at low flow rates results in wastage of electrical energy. It results in wastage of energy. What is the solution to this problem? The solution to this problem is to replace the conventional motor driven pump by modern motor driven pump. Let me write here, modern motor driven pump. In modern motor driven pump, we include power electronic converter also. So it is like this. We have a power electronic converter. This is PEC, power electronic converter. This is AC input or AC supply, which may be single phase or three phase. This power electronic converters gives supply to motor. So this is our motor, of course, AC motor. And the AC motor is coupled with pump. This is the pump. Same pump that we had used earlier, but the pump is now controlled by this mechanism. So this is the inlet, this is inlet, and this is outlet. This is outlet. Here we are not using any throttling valve for controlling the flow rate, because the motor is not a single speed motor, it is a variable speed motor. I write here variable speed motor. The frequency of the supply here is F, say 50 Hertz. And what this power electronic converter does, it may convert AC into DC and DC back into AC, but at variable frequency. Okay. So the power supply which is fed to the winding of the induction motor, it's at variable frequency. And at variable frequency, we know that the motor does not run at fixed speed, it runs at variable speed, because the speed of induction motor is directly proportional to frequency. As the frequency changes, the speed of motor changes. So instead of using fixed speed motor, we are using, or instead of using single speed motor, we are using variable speed motor. If the flow rate required is high here, what will this power electronic converter do? It will impress a voltage at rated frequency, at high frequency, so that the motor runs at rated speed and flow rate is high. If you want to reduce the flow rate, what this converter will do, it will decrease the frequency of the supply to the AC motor. The AC motor now receives voltage at reduced frequency, so its speed automatically gets reduced, because at low frequency speed is less and flow rate also automatically gets reduced. So instead of using throttling valve and closing the throttling valve for low speed, for low flow rates, we are just controlling the speed of the motor for controlling the speed of pump, and hence controlling the flow rate. Okay. So therefore, when the motor is, when the pump is having high flow rate, motor runs at rated speed. Okay. And the motor may draw rated power from the source. When the flow rate required is less, what happens? Motor runs at low speed, and since P is equal to omega t, when speed reduces, the power drawn by motor from the source also reduces. So it draws reduced power. So there is no wastage of power. This is contrary to traditional motor driven pump, in which case the motor was running at the same rated speed, even at low flow rates, and it was drawing the same amount of power as at high flow rates and wasting the power. In this case, at low flow rate, motor speed reduces, power drawn by motor from source automatically reduces. So therefore there is no wastage of energy, and hence there is a conservation, there is conservation of energy, which is resulted by this modern motor driven pump with the help of this PEC, that's power electronic converter. Okay, this can be explained also like this. Let omega m1, that let us assume that we run the motor at high flow rate. The pump requires high flow rate. So let omega 1 m1 be equal to omega. So therefore, what is power drawn by motor from the source? It is omega into t. P is equal to omega into t, speed into torque. Okay. For pump type of load, I am sure all of you know, for pump type load, what's the relationship between torque and speed? Torque is directly proportional to square of the speed. For constant torque load, torque is independent of speed. But for pump type of load and fan type of load and also blower type of load, this is the relationship between torque and speed. Torque is not proportional to speed, it is proportional to square of the speed. So therefore torque is proportional to square of the speed. If you substitute it here, let us call this power P1. So therefore P1 is proportional to omega cube, because for T you can substitute omega square. Omega square into omega is omega cube. Let's call this equation as equation 1. Now let us assume that we have to reduce the flow rate. For reducing the flow rate, what will power electronic converter do? It will reduce the frequency of the supply. So motor will run at reduced speed and flow rate will reduce. Let us assume motor runs at low speed. Let omega m2 be 1 by 2 omega m1, half of the speed. That is 1 by 2 omega. Okay. So therefore, the speed of the motor is now half what it was at high flow rate. So therefore, how much power motor will draw from the source? It is proportional to omega cube. But how much is the omega? Omega is not equal to, omega m is not equal to omega. It is half of the omega. So it is half of omega cube. So it is proportional to 1 by 2 cube means 1 by 8 into omega cube. Let's call this equation as equation 2. Dividing equation 2 by equation 1, you will get P2 by P1 is equal to 1 by 8 omega cube divided by omega cube. Omega cube where omega cube goes. So P2 by P1 is equal to 1 by 8. Which means when motor is run at a speed which is half of the rated speed, the power drawn by motor from the source reduces by a factor of 1 by 2. So therefore, if omega 2 is equal to half of omega 1, the power drawn P2 is equal to 1 by 8 P1. So this again shows that power drawn by motor or power drawn by the drive at low speed, at low flow rate, when you decrease the speed by half, the power reduces by a factor of 1 by 8. Hence, there is a lot of saving in the power. Okay. This same thing can be explained with the help of a numerical example. Let us take a simple numerical example. I will try to discuss with you and try to explain with the help of a simple numerical example. Let us assume that we have a 15 kilowatt example. 15 kilowatt motor driven pump. Motor driven pump. Let us take two cases. Case A is without power electronic converter. That is conventional motor driven pump. Okay. Let us assume the pump runs 300 days in a year, 300 days per year. And in a day it runs for 24 hours. All the time it is on and it is pumping the water continuously. And let us assume in a year 1200 cubic meter of water is pumped by the pump per year. Okay. Since the pump is without power electronic converter, it is a conventional motor driven pump. It's a single speed pump. It runs at same speed. For high flow rate, the throttling valve is open. For low flow rate, you partially close that and there is wastage of energy. Let us assume that the energy consumption is, let energy consumption be 0.36 kilowatt per cubic meter. So therefore, how much energy do we consume? So, and let us also assume that let cost of energy consumption be 8 cents. 8 cents means $0.08 per kilowatt hour. $0.08 per kilowatt hour. Let this be the cost of energy. So therefore, how much energy are we consuming in a year? So therefore, energy consumed by pump per year is equal to how much, what is the energy consumption? 0.36 kilowatt hour per cubic meter. So it is 0.36 kilowatt hour per cubic meter multiplied by how much, what is the total water we are pumping in a year? 1200. And how many days are there in a year? 300 days. So if you calculate it, it comes out to be 1,29,600 kilowatt hour. This is the amount of energy that this conventional motor driven pump is consuming from the source. Okay, so therefore what is the cost of energy consumed? What is the cost of energy? It is 1,29,600 kilowatt hours multiplied by what is the rate of energy. It is 8 cents, that is $0.08 per kilowatt hour. So multiply it by this. So this comes out to be $10,368 per year. So therefore the total cost of energy for conventional motor driven pump per year is $10,368. Okay. Now let us take case B. Very quickly we will take case B. In case B, we are using power electronic converter. That is modern pump. Modern motor driven pump. In modern motor driven pump, we have adjustable speed drive. We don't have fixed speed motor, we have variable speed motor. The power electronic converter controls the speed of the motor as per flow rate. For high flow rate, the speed of motor pump is high. For low flow rate, the speed of pump motor is low, and hence flow rate is controlled. There is no throttling value, and hence the energy consumption will be less. Let energy consumption be reduced. Let energy consumption be reduced from 0.36 kilowatt hour per 0.36 kilowatt hour to, let's say, 0.28 kilowatt hour per cubic meter. For conventional motor driven pump, the energy consumption was 0.36 kilowatt hour per cubic meter because there was wastage of energy at low flow rates, as already explained. But for modern motor driven pump, since we are not using throttling value, we are using speed control. For high flow rate, speed is high. For low flow rate, speed is low. So when speed is dropped, the energy consumption also reduces. So energy consumption reduces from 0.36 to 0.28 kilowatt hour per cubic meter. So therefore, what is the total energy consumed per year? Energy consumed per year is equal to 0.28 kilowatt hour per cubic meter. And how many cubic meters are we pumping in the year? 1200 multiplied by 300 number of days. And I have already calculated it. It comes out to be 1,800,000 kilowatt hour. So therefore, what is the cost of energy? Cost of energy consumed. How much energy you are consuming per year is equal to 1,08,000 kilowatt hour multiplied by $0.08 per kilowatt hour. I have already calculated it. It comes out to be $8,064 per year. $8,064 per year. For conventional motor driven pump, the energy consumption, the cost of energy per year is 10,368. And for modern motor driven pump using power electronic converter, it is reduced from $10,368 per year to $8,064 per year. So therefore, what is the saving in cost? It is 10,368 minus 8,064. So it is $2,304 per year. So in every year we are saving this much of amount, $2,304 per year. Okay, so this again explains how modern power electronic converter based electric drive, for example in this case motor driven pump, how it results in energy consumption, right? How it results in energy conservation, and hence saving in the energy, saving in the cost. However, when you are using a modern power electronic converter based drive, you have to incur or you have to invest on power electronic converter. This converter does not come free of cost. Let us suppose for this case, the cost of converter, let cost of power electronic converter be $8,000. Okay. How much is saving per year? Just few moments we have seen that by using power electronic converter based motor driven pump, we save $2,304 per year. So therefore, what is the payoff period? Payoff period is 4 years. That means within 4 years, the additional price that we have invested on procurement of power electronic converter for modern motor driven pump, which is $8,000. Every year we are saving approximately $2,304. So multiply it by 4, so it is approximately 4,000. So every year, so it will take approximately even less than 4 years to recover this money which we have invested over investment of power electronic converter. It will take just around 4 years to recover this. And what is the useful life of drive? Useful life of this drive motor driven pump, it is 15 to 20 years. That means for rest of the period, if for 4 years we are recovering this additional cost, for rest of the 11 years we will be saving every year at the rate of $2,304 per year. So this clearly tells us that although the initial cost of AC drive using power electronic converter is high, but it pays off in a few years, and in the long run it results in saving in energy and saving in the price of energy. This can also be explained with the help of a system. Let us suppose, again we'll take two cases. Case a thermal power plant. This is a thermal power plant. I will write here, this diagram for thermal power plant. At this thermal power plant, we are generating the electrical energy. The efficiency of this thermal power plant is very poor. It is just 0.4%. 40%, that is 0.4. Then this is the transmission line. This is transmission line. Through this transmission line, power is transmitted. The efficiency of this transmission system is 90%. Transmission system is highly efficient. Then we have distribution step-down transformer, and let us assume we use a load. Say, let us take same type of load, pump, and in the case A, we will take conventional motor-driven pump, and this is motor plus throttling valve, and then the efficiency of this motor and throttling valve is again very poor, just 40%. And then this is the pump. I will write here pump. The efficiency of pump is 75%, 0.75. Let us suppose the output power of the pump is 10 kilowatts. I mean, you need a power of 10 kilowatts to run this motor driven pump for pumping the water. This is the thermal power plant, this is the transmission system, and then this is the load. We'll consider only one type of load, that's motor driven pump. And this is the conventional motor driven pump, which comprises of motor plus pump with throttling valve. For controlling the flow rate, we are opening or closing the valve. Okay, so we are not using any power electronic converter for control of flow rate. We are using conventional method. Okay, this is the conventional motor driven pump. For producing an output of 10 kilowatt, what should be the input power to the pump? We know that efficiency is defined as output power by input power, P out by P in. So from this, what is input power? Input power is output power by efficiency. Output power of the pump is 10 kilowatts divided by what is the efficiency of this pump? 75%, 0.75. So this comes out to be 13.3 kilowatts. That means input power is 13.3 kilowatts. That means the input power to the pump is 13.3 kilowatts and it produces an output power of 10 kilowatts. And how much is the loss? Let me write here loss. Loss is 13.3 minus 10, that is 3.3 kilowatts. Fine. Now, what is the input to the motor? Now, motor along with the throttling valve has a very poor efficiency, only 40%. It does not mean motor is inefficient. Motor is highly efficient, but the throttling valve, which is a part of this pump, it results in wastage of energy, as I have already explained to you. At low flow rates, we are closing the throttling valve, but the motor draws same amount of power as at high flow rate, and hence it wastes the power. So therefore, the efficiency of the system is very poor, just 40%. So therefore, if output of this motor is 13.3 kilowatts, which is input to the pump, what is input to the motor? Using same formula, input to the motor is output, which is 13.3 kilowatts, divided by efficiency of motor plus throttling value 0.4. and I have already calculated it. It comes out to be 33.2 kilowatts. It is 33.2 kilowatts. This is the input to the motor plus throttling valve. So therefore, how much is the loss? Loss is 33.2 kilowatts minus 13.3 kilowatts. This is the loss. This is 33.3 minus 13.3. So this is 20 kilowatt. So there is a huge power loss in throttling valve. How much? 20 kilowatts. It's motor plus valve loss, but motor loss is very, very small. Most of the loss takes place in the throttling valve. So it is very, very large power loss, 20 kilowatts. Now let us go upstream. In the upstream, the transmission line efficiency is 0.9, that's 90%. At the output of the transmission line, input power to the motor is 33.3 kilowatts. What is the input power to transmission line, which is the output of this generator? So that is again using the same formula, P out by eta. Output power is 33.3 divided by eta. Eta is 90%. I've already calculated it. It is 36.9 kilowatts. That's around 37 kilowatts is the power input to transmission line. So therefore, how much is the loss from here to here? The transmission line input power is 37 kilowatt, which is the output of generator. And at the output of transmission line or input to the motor, the power is 33.3 kilowatts. So loss is 37 minus 33.3, and this is around 3.7 kilowatts. The loss is around 3.7 kilowatts. It's a small power loss because efficiency of transmission line is 90%. Now let's go to the thermal power plant. In the thermal power plant, you are burning the coal, producing the energy, and then you are producing steam. With the help of steam, you are running the turbine, but this is a very inefficient system. The efficiency is very, very poor, only 40%. So therefore, how much is the input power to the thermal power plant? Output power by efficiency, 37 kilowatt by 0.4, and it comes out to be 92.5 kilowatts. 92.5 kilowatts is the power input to the thermal power plant, and its output power is 37 kilowatts. So therefore, how much is the loss at the thermal power plant itself? Loss is huge figure. It is 55.5 kilowatt loss. Huge power loss. Okay. So which means that for driving a pump with a power rating of 10 kilowatt, how much power you need to generate at the thermal power plant? 92.5 kilowatt. So the input, mechanical input to the input to the thermal power plant has to be 92.5 kilowatt. For this input, you can produce an output of 10 kilowatt because there is huge power loss on the way. The main power loss takes place at thermal power plant itself, and then there is a small loss in the transmission line, and then big loss in the this motor driven pump throttling valve, so that efficiency is only 40%. So there is a power loss of 55.5 kilowatt here at thermal power plant, and a power loss of 20 kilowatt at the throttling valve of the motor driven pump. Okay, so therefore, what is the total overall efficiency of the system? Overall efficiency is output power by input power. Output power is 10 kilowatt at the pump, and input is 92.5 kilowatt. So this is approximately 11%. So the efficiency of this system for driving this 10 kilowatt pump is just 11%. That means for driving this 10 kilowatt pump, you need to have a power at the thermal power plant of 92.5%. So this gives a very poor efficiency, 11%. Can we improve the efficiency of the system? Yes, by using modern power electronic converter based motor driven pump. That I will discuss with you in case B. In case B, we are using modern motor driven pump. Modern motor driven pump. I will again draw this diagram. This is the thermal power plant. Efficiency is very poor, 0.4. This is the generator, and this is the step up transformer. This is the transmission line whose efficiency is very high, 0.9. Transmission network. Then we have distribution transformer, and then before the pump we have power electronic converter. This is the power electronic converter. Okay, plus power electronic converter plus motor. Okay, and then we have pump. The efficiency of power electronic converter and motor is very high, 80%. Whereas in the previous case, we were not using power electronic converter, we were using motor pump with throttling value. The motor and throttling value efficiency, especially throttling value efficiency, was only 40%. Now, since we are removing the throttling value, replacing that by power electronic converter, which will cause speed control of motor and hence control the flow rate without throttling value, the efficiency is enhanced from 40% to 80%. And pump efficiency is same, 75%, 0.75. Again, here output power of pump is same as in the previous case, 10 kilowatt. Input power to the pump or output power of motor is 33.3 kilowatt. Sorry, 13.3 kilowatts. So that there is, at the pump, there is a loss of 3.3 kilowatt. Understood. Now, what is the input to the motor, power electronic converter and motor? Output by efficiency. Output is 13.3 kilowatt. By what's the efficiency of power electronic converter and motor? 80%. It's very high. So input is 16.6 kilowatts. And how much is the loss? 16.6 minus 13.3. It is around 3.3 kilowatt loss. Okay. And then what is the input to the transmission line? Output by efficiency. Output is 16.6 by efficiency is 90%. So it is 18.4 kilowatt. And how much is the loss? 18.4 minus 16.6, it's around 1.8 kilowatt. Loss is only 1.8 kilowatt. And then what is the efficiency of thermal power plant? Only 4%, only 40%, 0.4. So therefore, what is the input? 18.4 by 0.4, and this comes out to be 46 kilowatts. And therefore, what is the loss? 46 kilowatts minus 18.4 kilowatts. So loss is 28.4 kilowatts. 28.4 kilowatts. So therefore, in this case, for producing an output, which is the power rating of the pump of 10 kilowatt, how much input you need? Only 46 kilowatt. Whereas in case A, where you were using conventional motor driven pump, you needed a power of 95 kilowatts. Here you need only 46 kilowatts. Why? Because you have not, the efficiency of thermal power plant is same as in the previous case, only 40%. Transmission line efficiency is also for 90%, same. Pump efficiency is also same, 75%, but we have improved the efficiency of the power electronic converter plus motor. I mean, the overall efficiency of this motor driven pump, which is now modern power electronic converter based motor driven pump, you have increased efficiency from 40% to 80%, and hence you have saved the energy. So therefore, what is the overall efficiency of the system? Output power by input power. Output power is 10 kilowatt by input power is 46 kilowatt. So efficiency is around 22%. So in the conventional motor driven pump where throttling valve was used, you remember just few moments back we have found efficiency was only 11%. And when we have replaced the conventional motor driven pump with modern power electronic converter based motor driven pump, it has doubled the efficiency. It has increased efficiency from 11% to 22%. Hence, there is substantial improvement in the efficiency of the system. So this clearly tells that these power modulators or power processors, which are nothing but power electronic converters, they are integral part of all AC and DC electric drives. They not only process the power, convert power from one form to another form, and they don't only result in torque control and speed control, but they also result in substantial energy conservation. So I hope this is clear to all of you. I will stop my today's lecture. More on it in next lecture. Thank you.